Good day, everyone. I am Shane B. Navarro, and together with Erica May Gonzaga, we will present our mathematical investigation entitled A Single Fraction Cross Multiplication Algorithm for Linear Equations with Fractional Coefficients. So, our investigation proves a new algorithm called the Single Fraction Cross Multiplication Algorithm, or SFCM, as an alternative method to the traditional least common denominator, or LCD method in solving linear equations with fractional coefficients. Linear equations are introduced in grade 8 mathematics, where students begin solving equations involving variables, integers, decimals, and fractions. Among these equations with fractional coefficients are often considered one of the most difficult because students must deal with both arithmetic and algebraic concepts at the same time. The traditional approach is to multiply every term by the least common denominator, or LCD, to eliminate the fractions. Although this method is mathematically correct, it combines two different skills. First, students must correctly determine the LCD through factoring or listing multiples. And second, they must correctly apply the properties of equality to solve the equation. So many students make mistakes during the first part because finding the LCD requires number theoretic reasoning, especially when the denominators become more complicated. So even when students who can solve equations with integer coefficients often struggle once fractions are introduced. So because fractions are unavoidable in mathematics, we asked whether there is another mathematically valid approach that avoids the error-prone process of finding the LCD. So this led us to investigate whether the familiar cross-multiplication technique used in proportions could be generalized and formally proven as an alternative algorithm for solving linear equations with fractional coefficients. So as a result, we developed the single fraction cross multiplication algorithm, or SFCM, and proved its validity mathematically and compared it with the traditional LCD method. So for the main research question of this investigation is, can the single fraction cross multiplication algorithm be derived, proved, and validated as an alternative to the traditional least common denominator method for solving linear equations with fractional coefficients? So to answer this question, we have examined 5 specific questions. So first, we investigated whether the algorithm can be derived directly from the properties of equality, and whether its closed form solution is algebraically equivalent to the traditional LCD method. Second, we asked whether numerical testing using equations with different denominators complexities support the algebraic proof. Third is we compared the SFCM algorithm and the LCD method in terms of procedural steps, computational complexity, and potential sources of error. Fourth is we identified the conditions under which the algorithm becomes undefined or loses its advantage. And lastly, we examined whether the algorithm can be generalized to equations with fractional coefficients on both sides and whether this generalized form correctly reduces to the original theorem. And as for the objectives of the investigation, the general objective of our investigation is to derive, prove, validate, and generalize the single fraction cross multiplication algorithm and evaluate it as an alternative to the traditional LCD method. So specifically, we aim to derive the algorithm step by step from the properties of equality and establish it as Theorem 1, and also to prove that its solution is algebraically equivalent to the traditional LCD method, and validate the algorithm using numerical test equations with increasing denominator complexity. and also to compare both methods in terms of procedural steps, computational complexity, and susceptibility to error. So, then determine the algorithm's domain restrictions and limiting cases, and extend the algorithm to equations with fractional coefficients on both sides, resulting in Theorem 2, and verify that it correctly reduces to Theorem 1. So this investigation is based on several important mathematical concepts. First is the linear equation in one variable, which has the form px plus q equals r and has exactly one solution whenever the coefficient of the variable is not zero. And second is the fractional coefficient, where the coefficient of the variable is expressed as a fraction. And third are the properties of equality, namely the addition, subtraction, multiplication, and division properties. So these properties justify every algebraic step used in both the traditional method and the proposed algorithm. So we also use the rule for adding unlike fraction, which allows two fractions to be combined into a single fraction. So another important concept is cross multiplication, also known as the means extremes property, which states that in a proportion that the product of the means equals the product of the extremes. So finally, we consider the least common denominator, which is the standard technique used in the traditional method to eliminate fractions. Although both methods rely on the same mathematical principles, they differ in how they remove the fractions. The traditional method uses the LCD, while the SFCM algorithm combines fraction first and then apply cross multiplication. So for the methodology, we have the materials for this investigation. So a scientific calculator for verifying computations, pencil, ruler, and paper for symbolic derivations and word solutions, and reference algebra textbooks together with the DepEd Grade 8 and Grade 10 Mathematics Learners module, and spreadsheet software to organize our computations and independently verify the formulas that we derived. So unlike experimental studies, this investigation is derivation-based and proof-based. So rather than data collection based. So the methodology consists of 5 stages, or the procedure consists of 5 stages. Stage 1 was establishing the notation and assumptions. We defined all variables and coefficients used throughout the investigation and assumed that all denominators are non-zero. So we also specified that each theorem applies only when the equation has a unique solution. Stage 2 is to involve deriving and proving theory 1, which is the single fraction cross multiplication algorithm. So starting from the original equation, we combine the fractional terms into one fraction using the addition rule for unlike fractions. Instead of finding an LCD across all terms, we applied cross multiplication. Every step was justified using the properties of equality, resulting a closed form solution called algorithm 1. So for stage 3, extended this idea to equations with fractional coefficients on both sides by applying the same combine then cross multiply strategy. So we derive and prove theorem 2. We also verified that setting the additional coefficients to 0 reduces theorem 2 back to theorem 1, confirming the internal consistency of the algorithm. And for the stage 4, it is focused on selecting test cases. We choose 5 equations representing different denominator structures: equations with shared factors, partial shared factors, pairwise co-prime denominators, a two-sided equation, and a degenerate case with equal coefficients. So each equation was solved independently using both the traditional LCD method and the proposed SFCM algorithm, and every solution was verified through substitution. So finally, stage 5, we establish the comparison criteria. We compare the two methods based on the 5 aspects: the number of procedural steps, the type of mathematical judgment required, the size of intermediate computations, whether additional simplification was needed, and the conditions under which each method becomes undefined or fails to produce a solution. So this systematic procedure allow us to derive, prove, validate, and fairly evaluate the proposed SFCM algorithm against the traditional method which is the LCD. So we have here the table 1, which is the symbolic derivation and proof of theorem 1, or the SFCM. So now I will explain how we derived and proved theorem 1, which is the foundation of SFCM. So step 1 is to combine the left side. So in this step, we combine two fractions on the left-hand side into a single fraction using the rule for adding unlike fractions. So instead of immediately finding the LCD for the entire equation, we only combine the two fractions that are already on the same side. So this is simply applying the formula for adding fractions with different denominators. So this creates one fraction that contains both terms. And for the step 2, we rewrite the equation. So after combining the fractions, we simply rewrite the equation. So nothing changes in this step. We are only expressing the left-hand side as a single fraction while keeping the equation equivalent. So this follows the transitive property of equality, meaning the equation still represents their same relationship. And for the step 3, apply cross multiplication. So since both sides are now expressed as fractions, we can apply cross multiplication, also known as the means extreme property. So instead of finding one least common denominator across all fractions, cross multiplication directly removes the denominators by multiplying the numerator of one fraction with the denominator of the other and vice versa. So this simplifies the equation while still preserving the equality. And for the step 4, we apply the distributive property. So the multiplication obtained from the cross multiplication is expanded so that every term is written separately. So this transforms the equation into a standard linear equation. So for the step 5, we collect the variable terms. So once the equation is expanded, we isolate the variable by moving all x terms to one side and the other constant terms to the other. So this uses the subtraction property of equality, which allows us to subtract the same quantity from both sides without changing the equality. And for the step 6, we solve for x. So after isolating this x term, we divide both sides by its coefficients. So this applies the division property of equality, giving us the value of x. And for the step 7 is we factor out the common factor from the numerator. And this produces the final closed form formula of theorem 1. So instead of repeating all the algebraic steps every time we solve an equation, this theorem provides one direct formula that can be used immediately. So the table 1 proves that every step of SFCM is justified by established algebraic properties. So the algorithm is not based on shortcuts or patterns. It is derived entirely from the properties of equality, making it mathematically equivalent to the traditional LCD method. So after proving theorem 1, we converted the proof into an algorithm 1, making it easier to use. So instead of repeating the derivation, the users or the student simply identifies the coefficients from the equation, substitute them into the formula, checks whether the denominator is 0, and if it is not, computes the value of x. So this transforms the mathematical proof into a practical solving procedure. And as for the table 2, the symbolic derivation and proof of Theorem 2. So, after establishing the Theorem 1, we investigated whether the same idea could be extended to equations that contain fractional coefficients on both sides. So, step 1, we combine both sides. So, the first step is similar to the Theorem 1. This time, however, we combine the fractions on both the left-hand side and the right-hand side using the rule for adding unlike fraction. So each side becomes a single fraction. And for the step 2, we cross multiply. Since both sides are now represented by single fraction, we again apply cross multiplication. Just like in the Theorem 1, this eliminates the denominators without using the least common denominator. For the step 3, we expand both sides. So, in this step, we then apply the distributive property to expand all products. So, this converts the equation into a standard algebraic expression. And as for the step 4, we gather the x terms. So, using the subtraction property of equality, all terms containing x are moved to one side, while all constant terms are moved to the opposite side. And for the step 5, factor the variable. Now, in this step, we factor out the variable x. This allows us to express the entire coefficients of x as one algebraic expression. And for the step 6 is we dividing to solve for x. So in this step, we divide both sides by the coefficient of x. So this gives the generalized closed form solution known as Theorem 2. So an important result of table 2 is corollary 1. By assigning 0 to the additional terms on the right-hand side, Theorem 2 automatically simplifies back into Theorem 1. So this demonstrates that the generalized theorem is mathematically consistent because the original theorem is simply a special case of it. So, algorithm 2 follows the same structure as algorithm 1. The user substitutes the coefficients into the generalized formula, computes the numerator and denominator, and checks whether the denominator equals 0. So, if the denominator is 0, the algorithm determines whether the equation has infinitely many solutions or no solution. So, otherwise, it directly computes the value of x. So this allows the same combine then cross-multiply idea to be applied to a broader class of linear equation. So, overall, the table 1 and 2 are the mathematical proofs behind our proposed algorithm. They show that every step follows the fundamental properties of equality, ensuring that the SFCM algorithm is not merely a shortcut but a rigorously derived method. Algorithm 1 and 2 then translate this proof into practical procedures that can be applied directly when solving linear equations with fractional coefficients.
Now that we've walked through how the SFCM algorithm was derived and proved, let's look at what happened when we actually put it to the test. We selected 5 equations and we didn't pick them at random. Each one was chosen to probe a different region of the algorithm's domain. The first 3 equations are one-sided, and they test Theorem 1 under increasing denominator complexity. Equation 1 has denominators 2, 3, and 6, where 6 is simply a shared multiple of 2 and 3, so the LCD is easy to spot. Equation 2 raises the difficulty slightly. Its denominators are 3, 4, and 2, and here the LCD, which is 12, is actually smaller than the full product of the denominators, which would be 24. Equation 3 is the hardest of the 3. The denominators 5, 7, and 9 are pairwise coprime, meaning they share no common factors at all. So the LCD ends up equal to the full product of 315. Equation 4 shifts to testing theorem 2, the generalized formula on a two-sided equation with denominators 3, 2, 4, and 6, comparing it directly against LCD clearing. And equation 5 is deliberately degenerate. Both sides have the same x coefficient. So AH equals GB, which means theorem 2's denominator vanishes. We included this one on purpose, not to get a clean answer, but to see how the formula behaves right at the edge of where it's defined. Across every case where a solution actually exists, both methods, the traditional LCD approach and the SFCM formula, produce exactly the same value of x. That agreement is the numerical confirmation of the algebraic proofs we presented earlier in the table 1 and 2. Let's zoom in on equation 3 because it's the case that stresses the traditional method the most. Using the LCD method, the first move is to find the LCM of 5, 7, and 9. Since those numbers are pairwise coprite, the LCM is their full product 315. From there, every term gets multiplied by 315, giving 189x plus 90 equals 140, which simplifies to 189x equals 50, and finally x equals 50 over 199. Now compare that to the SFCM root. We simply read off the coefficients. A equals B, A equals 3, B equals 5, C equals 2, D equals 7, E equals 4, and F equals 9. And substitute directly into the formula x equals B times the quantity of ED minus FC all over ADF. The numerator simplifies to 5 times the quantity of 28 and 18, which is 5 times 10 or 50. The denominator is just 3 times 7 times 9, which is 189. So we land on the same answer, x equals 50 over 189. But without ever having to hunt for a common denominator, we verify this by substituting the answer back into the original equation, and it checks out exactly. 3/5 of 50 over 189 plus 2 sevenths equal 4 ninths confirm. Equation 4 tests the generalized formula, theorem 2, on a two-sided equation. With the traditional method, we first find the LCD of all four denominators 3, 2, 4, and 6, which is 12. Multiply every term through and simplify down to 5x equals 4, giving x equals 4 over 5. With theorem 2, we identify all 8 coefficients A, B, C, D, G, A, H, E, and F directly from the equation and substitute them into x equals BH times the quantity of ED minus CF over DF times the quantity of AH minus GB. Working through the arithmetic, the numerator comes out to 48 and the denominator to 60, which reduces to 4 over 5. The exact same result. And again, back substitution confirms both sides of the original equations equal 31 over 30. What's worth pointing out here is that equation 4 has twice as many denominators to deal with as the one-sided equations. Yet, the SFCM approach still required only a single substitution. The generalization didn't add computational burden even though the equation itself got structural more complex. This table pulls everything together. Across all 5 equations, both methods required about the same number of major steps, 4 in every solvable case. But look at the column for the kind of judgment each step demands. Only equation 3 under the traditional method needed factoring judgment to find that 315 was truly the least common denominator. Under SFCM, 0 equations require that kind of number theoretic reasoning at any point. Equation 2 is the one case where SFCM comes out slightly behind because it multiplies straight through the denominators instead of recognizing the shared factor between 2 and 4. It produces the fraction 9 over 8 and reduced, needing one more simplification step that an alert traditional method user could have skipped. And equation 5 shows the two methods diverging in how they report failure. The traditional method hits a flat-out contradiction. 1/3 equals 2/5, which is obviously false. SFCM instead produces a zero denominator which signals the same thing, but only if the solver remembers to check for it. So what do these results actually tell us? The headline finding is this: the SFCM algorithm and the traditional LCD method requires approximately the same number of procedural steps to solve a linear equation with fractional coefficients. If we were only counting steps, there'd be no real story here. But the story isn't in the step count. It is in the kind of thinking each step demands. The traditional method's very first move is finding the LCD, and that's a number theoretic task. You have to factor or list multiples or otherwise recognize structure in the denominators. SFCM replaces that entirely. All a student has to do is identify the coefficients and substitute them into a formula that's already been proved correctly. There is no factoring judgment required anywhere in algorithm 1 or algorithm 2. That distinctions become most visible exactly where we'd expect it to. In equation 3, with its pairwise co-prime denominators, and in equation 4, where 4 denominators would have forced the traditional method to search for a common multiple across twice as many numbers. In both cases, SFCM simply constructs its denominator as a product of known values. It doesn't search for anything smaller. On the other hand, equation 2 shows the trade of working the other way. When denominators do share a factor, here 2 and 4, an alert user of the traditional method gets a smaller, tidier LCD of 12, while SFCM barrels through to a larger unreduced fraction, 9 over 8, and then needs an extra simplification pass. That's a genuine weakness, though it's a matter of avoidable extra arithmetic, not an error in the method. And then there's equation 5, which exposes a real difference in how the two methods signal that no solution exists. The traditional method arrives at a manifestly false numerical statement, impossible to mistake for a true one. SFCM, by contrast, signal failure only through a vanishing denominator, and the student who forgets to check that condition risks evaluating an indeterminate 0 over 0 expression as if it were a real answer. So checking the denominator has to be built in as an explicit non-optional step in the algorithm. Weighing all of this together, SFCM's strength are its uniformity, the same two steps regardless of how many terms of denominators are involved, its elimination of number theoretic reasoning, and the fact that it's been proved, not just observed, to match the traditional method. Its weaknesses are that it can't take advantage of shared common factors. It's less transparent when an equation has no solution, and so far it only applies to single variable linear equations, not systems. Put simply, SFCM shines with large co-prime or many-term denominators, and it loses a little ground exactly where the traditional method has an easy shortcut available. Coming back to where we started, our research question asked whether a single fraction cross-multiplication algorithm could serve as a proven, general alternative to the LCD method. Based on everything we've just talked through, the answer is yes. Theorem 1 was derived entirely from the properties of equality and gives us the closed form solution x equals b times the quantity of ED minus FC over ADF. Theorem 2 extends that result to equations with fractional coefficients on both sides, giving x equals bh times the quantity of ED minus CF over DF times the quantity of AH minus GB. And it collapsed back into Theorem 1 exactly when G equals 0 and H equals 1, which is the internal consistency check we called corollary 1. All 5 test equations run through both methods produce identical results wherever a solution existed, and back substitution confirmed every one of them. All 6 of our specific objectives were met. We derived the algorithm, proved it, tested it numerically, compared it rigorously against the traditional method, identified exactly where it breaks down, and generalized it to two-sided equations while confirming the generalization behaves correctly. So, for both the original form and the generalized form, SFCM is a valid, proven, and equally accurate alternative to the LCD method. It's simpler, but in one precise sense only, not in raw step count, but in replacing a number theoretic judgment call with a single uniform substitution, with the trade-off that it gives a less transparent signal when no solution exists. Before we move to our recommendations, we wanted to share a bit about what this process was actually like for us. The hardest part, honestly, was proving Theorem 1 and Theorem 2 in general form rather than for specific numbers. It means tracking exactly which property of equality justified every single line, and for Theorem 2 in particular, factoring out terms like HFAD minus BDGF into DF times the quantity of AH minus GB took real care. Working through these proofs deepened our understanding of multi-step equations in general. We came away seeing clearly that the real complexity in solving these equations isn't the arithmetic. It's applying the correct property of equality at each step. This project also gave us practice in symbolic generalization, proving something true for all integers rather than for one example, and in designing a fair criteria-based comparison, which meant agreeing in advance on what counts as a step and what counts as a domain failure before we ever tested a single equation. One of the most rewarding moments was discovering at the level of the algebraic identities themselves exactly how Theorem 2 simplifies into Theorem 1. And one of the more humbling moments was realizing that the vanishing denominator is a subtler kind of domain restriction to watch for than an outright forbidden value. It's easy to miss if you're not looking for it. Based on what we found, we'd like to offer 6 directions for future work. Number 1. Extend to more complex rational equations. The proof strategy behind Theorem 2 could be extended to equation with more than 2 fractional x terms and to rational equations where the variable itself appear in a denominator. Number 2. Extend to systems of equations. The algorithm could be extended to solve systems of 2 linear equations with fractional coefficients, expressing the solution as a ratio of determinants in the same spirit as Theorem 1 and 2. Number 3. Implement it as a tool. Algorithms 1 and 2 could be implemented as a short spreadsheet formula or Python function that takes the coefficients as input, checks the domain condition automatically, and alerts the user with a clear message: no solution or infinitely many solutions, instead of an error. Number 4. Test on a larger, more varied set of equations. Future testing should include negative coefficients and larger denominators to see whether the trends we observe in Table 6 continue to hold at scale. Number 5. Run a classroom-based follow-up study. Since this investigation was primarily theoretical, an actual classroom assessment comparing errors rate and time on task between the traditional method and SFCM would tell us whether the theoretical advantages translate into a real learning benefit. Number 6. Explore applications beyond the algebra classroom. Finally, the combined then cross-multiply strategy at the heart of SFCM might have value in ratio and proportion problems more broadly, mixture problems, conversion problems, and other contexts that can be expressed as proportions. We hope that this investigation contributes to the development of more efficient mathematical strategies and serves as a foundation for future studies that will further improve the teaching and learning of algebra. That concludes our presentation. Thank you very much for your time and attention.